Hello guys, so in this video, in this video series of 100 days of TensorFlow developer certification program, day 2, I'll be doing a basic text classification from official TensorFlow documentation tutorials. So let's go ahead and start implementing it. Okay. Let me just give it name. Okay. So let's just go ahead and read it through. So this tutorial demonstrates text classification starting from plain text files stored on disk. You'll train a binary classification to perform sentiment analysis on an IMDb dataset. At the end of the book, there is an exercise for you to try in which you'll train a multi-class classifier to predict the tag for a programming question on Stack Overflow. Okay. So let's just go ahead and import the libraries. Okay. Import OS, import regular expression, import stripil, import string, import TensorFlow STF, and then from TensorFlow.keras import layers, TensorFlow.keras import losses from TensorFlow.keras, import preprocessing as well, and then from TensorFlow.keras.layers experimental.preprocessing import text vectorizer vectorization. Okay. Let's see. Okay, let's go ahead and print the TensorFlow version we are using. Okay, so sentiment analysis. This book trains a sentiment analysis model to classify movie reviews as positive or negative. Yeah, so it's a binary classification based on the text of the review. Okay, so this is an example of binary or two-class classification, an important and widely applicable kind of machine learning algorithm. Yes. Okay, so we'll be using large movie review dataset that contains the text of 50,000 movie reviews from the internet movie database. Okay, let's see. Okay, IMDb internet movie database. Okay. Yes. So these are split into 25k reviews for training and 25k reviews for testing. The training and testing sets are balanced, meaning they contain an equal number of positive and negative reviews. Okay, so yeah, so guys, this is the data set, right? So let's go ahead and see the next step. So let's just download and explore the database data set, right? So let me grab the URL. Or you know what, let's go ahead and take it from here, right? Okay, now data set will be tf.keras.details.get file. We can give it a name of ACL IMDb v1 URL. We wanna unzip it, untar it, and we wanna cache the directory in current directory, right? And we wanna cache subdirectory as well. Okay, so after that we wanna create the dataset directory with os.path.join os.path.name of dataset, right? And we wanna join it with this one. Okay, let's see. Downloading the dataset. Okay, so let's just list the files folders in the dataset directory, right? It's running this one. After this, It's gonna run this one. Okay. Okay. So yeah, you can see readme train test imdb.backup and imdb.txt. Okay, these are the file contents in this dataset directory, right? So let's just also create and create the chain directory. Okay, this one chain folder, right? So we want to join the path with chain folder and list was the content of chain directory. Okay. We can see the directory content of chain directory is your libs, this one, features, right? Okay, so the dataset train part of speech and POS and this train positive or negative. Okay, so these are the folders for positive and negative training dataset, right? Directories contain many text files, each of which is a single movie review. Let's take a look at one of them, right? Let's just take a look at the sample file. Okay, os.path.join chain directory, and we want to go to positive directory and look at a random text, just this one, and with open sample file as a we wanna read it. Okay, let's see the content of it. So yeah, this is one movie review, right? Okay. Okay, so let's load the data set. So next we'll load the data of disk and prepare it into a format suitable for training. To do so, we'll use the helpful text dataset from directory utility, which expects a directory structure as follows. Okay, let's see the documentation for it. Okay, so what it does is generates a tf.data.dataset from text files in a directory, and it takes directory structure, tables, label mode, class names, and this bunch of different parameters. Okay, and it takes directory structure as this one, class A, which we have positive, negative, and bunch of text here, right? So then calling text data set from directory main directory level inferred, it will return a tf.data.dataset which yields batches of text from the subdirectories class A and class B, which in this case positive and negative, right, together with labels 0 and 1 corresponding to class A and class 1 corresponding to class B, right? Okay, so let's go ahead and see. So to prepare dataset for binary classification, we'll need two folders on disk corresponding to class A and class B. These will be the positive and negative movie reviews, which can be found in this, right? Positive and negative reviews, right? As the IMDb dataset contains additional folders, you will remove them before you using this utility. Okay, so this additional folder it contains, right? So let's just remove this. imc remove the directory. Okay, so once that's done, so next we'll use the text dataset from directory utility to create a labeled tf.data.dataset, right? tf.data is a powerful collection of tools for working with data. Okay, so when running a machine learning experiment, it is best practice to divide your dataset into 3 splits, right, which is train, validation, and test. Okay, so in the IMDb dataset, has already been divided into train and test, but it lacks a validation set, right? So let's create a validation set using an 80-20 split of the training data by using the validation split. Okay, so let's just first create the batch size of 32. set the seed to 42. Draw train dataset tf.keras. Pre-processing will call text dataset from directory. We'll give it our directory name, right? Is this. We'll give it a batch size of batch size. We'll give a validation split of 20%, and we'll give a subset training and set the seed to 42, right? Okay. Okay, so it's completed, right? So let's just, so now as you can see above, there are 25,000 examples in the training folder with 2 classes, right? Of which we'll use 80%, which is 20,000 for training, right? And we'll see in a moment that we can train a model by passing a dataset directly to model.fit. If you're new to tf.data, you can also iterate over the dataset and print out a few examples as follows, right? Let's go ahead. We are new to the TensorFlow, right? So let's just take text batch and label batch from raw train ds, right? We'll take one batch, and for I in range 3, we'll just print each of them, right? Text batch dot numpy ith index and print label for it, label batch dot numpy ith index. Okay, yeah, so I think 0 is the negative one, 1 is the positive. Okay, this is the level for it. Okay, so here they're saying that the review contains the reviews contains raw text with punctuation and occasional HTML text like bracket, break line. You will show how to handle this in the following. You will be shown how to handle this in the following lesson, right? Levels are 0 and 1. To see which of these corresponds to positive and negative movie reviews, you can check the class names accordingly. Okay, so let's just go ahead and check the class name for it. Okay, level 0 corresponds to raw train ds, class name 0. Level 1 corresponds to raw train ds, class names 1. Let's see. So level 0 corresponds to negative and level 1 corresponds to positive, right? As we saw earlier. Okay, so next we'll create a validation and test dataset, and we'll use the remaining 5,000 reviews from the training set for validation, right? So here they're saying note, when using the validation split and subset arguments, make sure to either specify a random seed, right, or to pass shuffle equals to false, so that the validation and training splits have no overlap. Okay, yeah, so that's a good practice. Okay, so let's just complete this one and get our validation dataset for test dataset, right? Keras preprocessing for text dataset from directory, and IMDb train batch size validation is split of 20% and subset to be validation and set the random seed to be seed. Okay. Okay, so let's create same for testing dataset. Dot sds here dot ps dot preprocessing dot test dataset from directory text dataset from directory tcl imdb test, then set the batch size to the batch size. Okay, so we are getting 25,000 text belonging to two classes for test dataset. Okay, so here the pre-processing API is using the following section are experimental TensorFlow 2.3 and subject change. Okay, it's just enough. So prepare the dataset for training. Okay, so next we'll standardize, tokenize and vectorize the data using the helpful pre-processing.text vectorization layer. Okay, let's see the documentation. Okay, what it does, text vectorization layer. This layer has basic options for managing text in a keyless model. It transforms a batch of strings, one sample, one string, into either a list of token indices, 1D tensor of integer token indices, or a dense representation, 1D tensor of float values representing data about the sample tokens. Okay, let's take example. Text data set. This toolbar does the maximum vocabulary size 5,000, maximum length 4, sequence length prepared outputs this. Embedding dimensions 2. Okay, vectorizer layer, maximum tokens, maximum features this. Output mode int, output sequence maximum length 4. Okay, so this is the output. This is the output from model. Okay, what example they have? This vectorizer layer dot get vocabulary. Okay, unknown earth, wind and fire. Okay, let's just go ahead and run it and see. So standardization refers to pre-processing the text, typically to remove punctuation or HTML. Okay, elements to simplify the dataset. Tokenization refers to splitting strings into tokens. Okay, for example, splitting a sentence into individual words by splitting on white space. Okay, and vectorization refers to converting tokens into numbers so they can be fed into a neural network. All of these tasks can be accomplished with this layer. Okay, vectorization. So they are saying that we can basically convert each word into a we can basically represent each word as a vector of numbers, right? So that we can fed it into neural network. Okay, so as you saw above, reviews contains various HTML tags like this. Yep. Okay, this text will not be removed by the default standardization in the text vectorization layer. Okay, which converts text to lowercase and restricts punctuation by default but doesn't strip HTML. Alright, okay, so you write a custom standardization function to remove the HTML. Okay, okay, so here's some note to prevent int SSQ, also known as strange survey. It's important to pre-process the data identically at train and test time, right? So to facilitate this, the text vectorization layer can be included directly inside your model. Yep, as shown later in this tutorial. Okay, so let's just implement this text custom standardization. I mean, basically pre-processing the dataset, right? The text. So define custom standardization. Right, input data. We'll first convert it into lowercase. tf.strings.lower input data, and then we're gonna strip HTML, right? Stripped all the HTML tags. There is right. So tf.strings.regex replace lowercase, right? We're gonna replace every break tag to space, right? So and then let's just return the tf.strings.regex replace strip HTML percentage s this re dot escape string dot punctuation. Okay, and then it's just this. Okay, so I think we need to see this documentation for it. Okay, replace elements of input matching regex pattern with rewrite. Okay, let's see example. Okay, so here's the example. Text with this, replace all of this with space. Okay, so yeah, it just replaces everything, this one, and this one. Okay, yeah, okay, so this will be HTML and this will be string matching, right, like this one, and we're gonna replace it with nothing, right? Just empty string. Okay, and return it. Okay, good. So next we'll create a text vectorization layer. We'll use this layer to standardize, tokenize, and vectorize our data. And you set the output mode to int to create unique integer indices for each token. Okay, so note that you're using the default split function and the custom standardization function you defined above. Okay, yeah, this one, and you'll also define some constants for the model, like an explicit maximum sequence length. Okay, for LSTM layer, I guess, which will cause the layer to pad or truncate sequences to exactly sequence length. Okay, so it's just the sequence length of the vector. Okay, so let's just define it. Max features we're gonna take is 1000, 10,000. Sequence length is 250, and we have our vectorized layer, text vectorization, standardize. First we want to pass our custom standardization function, right, and then we want a maximum tokens of maximum features length, and we want the output mode to be int, and our output sequence length is sequence length. Okay, so next we'll call adapt to feed the state of the pre-processing layer to the dataset. This will cause the model to build an index of strings to integers. Okay, so here's some note. It's important to only use your training data when calling adapt. Okay, using the test set would leak information. Okay, all right, good to know. So let's get a train text, raw train ds, and we're gonna lambda xy to x. Okay, and then we're gonna pass it to vectorized layer dot adopt and train text. Okay, let's see what it does first. Okay, map data set. Okay, so can I take one? Okay, take one shape name. What's the content here? Okay, so we are mapping this one, right? What's the content of this? Okay, take one. Okay. Oh. Okay. Take one and then xy. A data set has no attribute. Okay, so type of x is it's a text data set. Okay, so what we had done here, we took it text batch, label batch, and it was returning text batch and label batch, right? So it will be first will be a text, right? So what we have done here is what we're done here is this, we are mapping this one, right? Okay, so and we are passing it to our vectorizer layer. Okay, so let's move on to the next and then see what's happening there, right? Let's create a function to see the result of using this layer to pre-process some data. Okay, vectorize text level, text equals to expand dimensions, this, and then return vectorized layer of text label. Okay, so let's retrieve a batch of 32 reviews and labels from the dataset. Text batch, label batch, next iter dot nds, and then first review, first label equals to text batch 0, label batch 0. Okay, yep, and then print review, first review, and label dot nds dot class names first label, and then vectorized preview, vectorized text first preview and first preview. Okay, let's see. Okay, we have this text, we have this is a negative preview, so 0, and this is the array. Y is 1. Okay, Let's run it again. See. Okay, so it's different now. What about next one? So it's 1 and 0 only. Okay. Have we made any mistake here? I don't think so. Okay, let's just go ahead and we'll see if it throws any error. Okay, so as we can see above, each token has been replaced by an integer, and we can also look up the token string that each integer corresponds to by calling this vocabulary. Okay. Oh, okay. Okay. So vocabulary, right? Yeah, this one. Standardization, this output sequence length, this maximum features, we wanted this one, sequence length to be 250. Should be different, no? Right, this is different every time. Why it's 1 and 0 only? Let's debug something. So the error is coming here, right? First review, first label, okay. Text batch, label batch, dot train layers. Oh, okay. We had we were running some tests earlier. That's why I think um, that the wrong result is coming. Okay, so let's just rerun it again. Okay, see it. Okay. See, there we go. Okay. Okay, so yeah, so so we can get the vocabulary here. Let's get the 287. Let's get this one. What does this mean? Okay. We wanna vectorize layer, get vocabulary, right, of this. Okay, and also we want to see, let's say this one. Okay. Let's go with 404. Okay, let's see if it founds it or not. Get vocabulary 404. Okay, and let's print the vocabulary size. Length vectorize layer, get vocabulary, and yes, it's just a length, right? Okay, see, so this one corresponds to speak, and this speaks, this one corresponds to finally. Okay, and then vocabulary size is this. So 404 finally found out, right? Okay. Okay. So moving on to the next point, you are nearly ready to train your model. As a final pre-processing step, you will apply the text factorization layer you created earlier to train, validation, and test dataset. Okay. So let's create our train and training dataset, converting our raw text to integer. Right. Raw train ds map vectorized text validation data raw validation ds map vectorized test, and we want to test ds raw test ds map vectorized test. Okay. Configure the dataset for performance. Okay, let's configure the dataset for performance. Okay, so we're gonna be seeing some advanced TensorFlow use cases in order to improve the performance of IO operation. Right, so these are the two important methods you should use when loading data to make sure that IO does not become blocking. Okay, first one is dot cache, which keeps data in memory after it's loaded off disk. So this will ensure the data set does not become a bottleneck while training your model. And if your data set is too large to fit into memory, you can also use this method to create a performant on disk cache, which is more efficient to read than many small files, right? Okay. And then prefetch, what it does is it overlaps data pre-processing and model execution while training. Okay, so and we can learn more about these two methods, and as well as how to cache data to disk right here. See. Okay, so this is the API. Here are a bunch of examples. Here they show the benefits of prefetch, execution time here, right? So yeah, very interesting stuff, guys. I would highly recommend to read through it, right? So let's just go ahead and for this example, let's just go ahead and continue. Okay, so we'll first define auto tune, which will tune the number of buffer size automatically for us, considering the number of CPUs cores we have, right? Train ds cache prefetch buffer size to set to auto tune. Okay, same goes for ds validation dataset, validation ds cache sheet prefetch buffer size set to auto tune. Then same goes for test ds cache prefetch buffer size set to auto tune as well. Okay, so we have our data sets, and let's create the model, right? So we'll set the embedding dimension to 16, right? And then we'll our model tf.keyrest sequential, right? We'll first take our embedding layer, which will have good shape of maximum features +1 and embedding dimension, which is 16, and then we'll add a dropout layer with 0.2 probability, which will drop all the connections. Like if there's 100 connections, then it will drop 20 of the connections, right? That's the probability for dropping the connections. And then we'll add global average pooling 1D, so we're dealing with 1D data vector, right? So let's add a dropout layer as well, and then let's add our classifier layer, which is output layer with node 1, right, which outputs 1 or 0. Okay, so and let's just see our model summary, right? Okay, there's been a spelling mistake. Okay, so this is our model summary. Here we have 160,016 training parameters for our embedding layer, and 17 parameters for dense. Okay, so here's the detail of the layer. So let's go through it. The layers are stacked sequentially to build the classifier. The first layer is an embedding layer. This layer takes the integer and encoded reviews and looks up an embedding vector for each word index. These vectors are learned as the model trains, right? The vectors add a dimension to the output array, and the resulting dimensions are batch, sequence, embedding. To learn about embeddings, see the word embedding tutorial, which will go here, which we'll see here at word embeddings. Okay, so next, a global average pooling 1D layer returns a fixed length output vector for each example by averaging over the sequence dimension. Okay, this allows the model to handle input of variable length. All right, so in the simplest way possible. Okay, yeah. Okay, and then the this fixed length output vector is piped through a fully connected dense layer with 16 hidden units. Don't see any 16 hidden units. Okay, it's just the embedding dimension, I guess. Yeah. Then the last layer is densely connected with a single output node. Okay, so let's compile our model with loss function and optimizer. So a model needs a loss function and an optimizer for training, since this is a binary classification problem, and the model outputs a probability, a single unit layer with a sigmoid activation. So we'll use losses.binary cross entropy loss function, and now configure the model to use an optimizer and a loss function. Okay, so let's just go ahead, model.compile losses.binary cross entropy on logics true. Optimizer, we're gonna use Adam optimizer, and then matrix, we're gonna set matrix dot binary activation threshold 0. Okay, let's compile our model has been compiled, and now just let's train the model, right? We'll train the model by passing the dataset object to fit method, right? Let's train it for 10 epochs, and history model.fit train ds, validation data will be validation ds, and epochs will be epochs, right? Okay, so it's training. Let's wait for it, and then we can evaluate our model. So let's we're going to see how our model performs after evaluating it, and then the two values will be returned, right? The loss and accuracy, which represents our error, and which in this case, in the case of loss, the lower values are better, and accuracy, the higher values are better. Okay, for accuracy. Okay, almost done training. It's a binary class. Accuracy is training accuracy is 91%, and validation accuracy is 87%. I think it's quite good, but there's a small overfitting, but I think it's good. Okay, so yes, they say so let's just first evaluate our model test data set. Okay, loss accuracy model dot evaluate test ds, and we're gonna print the loss. Accuracy. Okay, let's see. So yeah, the results are matching. Okay, so yeah, so it's achieving around 87% accuracy. And so let's just create a plot of accuracy and loss over time. So model.fit, this returns a history object that contains a dictionary with everything that happened during training, right? So we can just go ahead and see the content of history. See here, contains the dictionary of everything that happened during the training, like epochs, within 0 to 9 epochs, right? History, binary accuracy, this much, loss, right? And it's in the dictionary, right? Well, we have validation accuracy as well. We have model parameters. Epoch 10 steps took was 625. Yep, 625 steps. Verbose was set to 1 by default, and validation data, there wasn't any validation data, right? Oh, there was a validation data, but it's saying none. Testing. Okay, let's go ahead and get our predict, and then we can print the keys of it. We have loss, binary accuracy, validation loss, validation binary accuracy, validation loss, validation binary accuracy, and loss, right? And binary accuracy. Okay, so let's just go ahead and plot it, right? So here they're saying there are 4 entries, one for each monitored metric during training and validation. We can use this to plot the training and validation loss for comparison, as well as the training and validation accuracy. Yes guys, these are numbers, so yeah, we can definitely plot it. So let's go ahead and plot it, right? First get the accuracy, binary accuracy, right? Get the validation accuracy, predict validation binary accuracy, right? Get the loss, predict loss, and validation loss is predict validation loss. Okay, so let's take range of accuracy +1, right, epochs, and then we'll plot epochs across x and y, PO equals training loss, okay. And then we're gonna plot and validation loss, the label validation loss, and then we're gonna set the title to training and validation loss and set the x label to box and set the y label to loss and show the legend, right? Let's just show the image. Okay, yeah, so I think, yeah, the model, I mean, the loss plot looks good. So there was some overfitting here, but so far the model, the training was good, right? For training loss, it kept converging, but for validation loss, after a while, after epoch 8 or after epoch 6, just diverged from the training loss, but it was still quite good. Okay, so let's plot the accuracy plot. Label training accuracy plot box, validation accuracy, and two, and we're gonna set the label as validation accuracy, and then we're gonna set the title as training and validation accuracy, right? Set the label as box and set the y label as accuracy and show the legend, right, at lower at location. Then just show the image. Okay. So yeah, the same scenario is same cases with the training accuracy, right? So here they are. No, let's read the description for the plot, right? In this plot, the dots represent the training loss and accuracy. Okay, training loss and accuracy, the training accuracy, and the solid lines are the validation loss and validation accuracy. Okay, so notice the training loss decreases with each epoch. Yep, and the training accuracy increases with each epoch. Okay, yeah. This is expected when using a gradient descent optimization, right? It should minimize the desired quantity on every iteration, right? This gradient descent optimization, they're referring to Adam optimizer, which we compiled our model with, right? This one. Okay, so it's Adam is just the modification of gradient descent optimization algorithm, right? So yeah, so next is saying that this isn't the case for the validation loss and accuracy, right? Yeah, we can see that the training loss was converging and loss was decreasing and the accuracy was increased, but wasn't the case for validation loss and validation accuracy, right? So in this case they seem to peak before the training accuracy, right? This is an example of overfitting. Yeah, we talked about it earlier, right? The model performs better on the training data than it does on data it has never seen before, right? So after this point, the model over optimizes and learns representations specific to the training data that do not generalize to the test data. This is the overfitting, guys, right? Model learns so good there in the training data that it over optimizes itself with the training data, but doesn't generalize itself for the validation data, right? So for this particular case, we could prevent overfitting by simply stopping the training when the validation accuracy is no longer increasing, right? For this we can use early stopping callbacks with tf.keras.callbacks.early stopping. Okay, so with that being said, let's just go ahead and export the model. Okay, So in the code above, you apply the text vectorization layer to the dataset before feeding text to the model. So if you want to make your model capable of processing raw strings, for example, to simplify deploying it, you can include the text vectorization layer inside your model. Yeah. And to do so, you can create a new model using the weights you just trained, right? So let's just go ahead and follow this steps to export our model and include text vectorizer, right? Sequential, so vectorize layer model and layers dot activation at a sigmoid, because we are using binary classification, right? So let's compile our export model. We're gonna set the losses dot binary cross entropy, and set the losses to true, false, and we're gonna use optimizer Adam, and what else, accuracy. Yeah, we're gonna use accuracy as our matrix. Okay, so let's just evaluate our model on the test data set. Export model log, evaluate test ds, and let's just print the accuracy. Okay, so guys, there was a typo here. Let's fix it. Another typo. What happens? Sequential object has no attribute. Evaluate. Okay. Another typo. Evaluate. Okay. Evaluate. Okay. Let's see. So around the same accuracy, right? Okay. Let's run inference on new data, right? So let's just gather some examples. The movie was great, and the movie was okay, and the movie was terrible. Okay, so let's run inference on our model, with our model, right? So see, samples, see here, right? So these are the prediction for this, right? It's predicting 58% is, let's see what they're describing. Including the text processing logic inside your model enables you to export a model for production that simplifies deployment and reduces the potential for train test skew, right? So there is a performance difference to keep in mind when choosing where to apply your text vectorization layer. Using it outside of your model enables you to do asynchronous GPU processing and buffering of your data when training on GPU. So if you're training your model on the GPU, you probably want to go with this option to get the best performance while developing your model, and then switch to including the text vectorization layer inside your model when you're ready to prepare for deployment. Okay, so with this tutorial to learn more about training models. Okay, okay. Yeah, so I think this is the task, right? Exercise. Okay, so let's just do the exercise. Okay, so exercise multi-class classification on Stack Overflow questions. So this tutorial showed how to train a binary classification binary classifier from scratch on the IMDb dataset. As an exercise, you can modify this notebook to train a multi-class classifier to predict the tag of a programming question on Stack Overflow. Okay, a dataset has been prepared for you. Okay, to use containing the body of several thousand programming questions. For example, how to sort a dictionary by value in Python. Posted to Stack Overflow. Each of these is labeled with exactly one tag, either Python, C Sharp, JavaScript or Java. Your task is to take a question as input and predict the appropriate tag, in this case Python. The dataset you will work with contains several thousand questions extracted from the much larger public Stack Overflow dataset on BigQuery, which contains more than 17 million posts. Okay. After downloading the dataset, you will find it has similar directory structure to the IMDb dataset you worked with previously. Okay, so I think it's we can do multi-class classification, and here they are saying they're giving a hint. So here's a note: to increase the difficulty of the classification problem, consists of the words Python, C Sharp, JavaScript or Java is the programming questions have been replaced with the word blank, right? As many questions contain the language they are about. Okay, so to complete this exercise, you should modify this notebook to work with the Stack Overflow dataset by making the following modifications. Okay, so at the top of your notebook, update the code that downloads the IMDb dataset with the code download this that has been prepared as the Stack Overflow dataset on the similar directory structure, and you will not need to make many modifications. Okay, so let's just go ahead and see. Let's see. Exercise. Okay, so let's paste it here, get the data set, change the link, add this one and give it Stack Overflow. Okay, let's see. Downloaded the dataset dir, and then modify the last layer of your model to read these four lines. Okay, what we can do is, let's just remove it and copy it. Copy this one, right, and then make modification here. Let's do the modification here as modify it, right? Go ahead, do this, right? Run as a list dir, Stack Overflow, no such file or directory. Okay, okay, dataset dir. So okay, okay, so it should be this one, right? what were doing. Oh, okay. So what was the directory structure for it? Let's just go to the, this one, directory name, this one. Okay, current directory. Okay, data set, list dir, users file or directory, this one. Okay. Okay. And so what we basically need is okay. All right. We downloaded it. We get the data set. We save it, right? Path and this. We're just joining it, right? What the data set. This one. Data set. Okay. Okay. We have this. We have name with this one. No, it's a sample data. Okay. So okay, so we just get train and test data, right? That's it, right? Okay. Test. Okay. Train. Okay. What we can do is we can look at the documentation. Let's see what it does. File name origin antar, right? True. This file hash cache subdirectory datasets. Okay, cache algorithm this. So let's just give it a same name as this one, right? Okay. We'll have folder of this. And we'll have trade and testing dataset here. Okay. See here, train and test dataset. Okay. So okay. Now let's list directory. Wow. Okay, train and test. So let's list it, right? And then what we do is, you know, this one. So we got the data set, right? We need to pre-process it, this one. Then we need to remove this one. Let's just remove it. Well, it's not a directory, right? Let's just do the okay. And now we'll do the same thing, but here we'll change it to this one. Training data, train, right? And then we can just do the same thing here, right? 1, 3, we can see the labels as well, right? You can also do 0, 1, 2, 3, right? So you can probably do 2 as well. Level 2 corresponds to which one? Okay, and then we have level 4 as well, I think, which is index wise level 3 with Python. Okay, and let's just see the length of the class name. 4 classes, right? Level 1 to 3. Okay, so let's get the validation data set. Okay, right, and then get the test data set. Okay. We don't want to replace this one, I think, or should we? I think we should, maybe we should do that, right? Let's do this, do this as well, and then also run it. Why not? This set blank quick on exception. I'm using blank days, looking around, label Python, right? So let's see just random vector what it corresponds to. Okay, so this will appear, this one. Okay, so let's just convert, right, auto tune it. Okay, yeah. Here we need to set the 4, right? Dense 4. Okay, 4. Okay, all right. And then when compiling the model, change the loss to sparse categorical cross entropy. Yeah. Okay, so losses dot sparse categorical cross entropy. This is the correct loss function to use for a multi-class classification problem when the labels for each class are integers. In this case they can be 0, 1, 2, 3. In addition, change the matrix to accuracy. Yeah, we don't need binary accuracy, we just need the accuracy. Since this is a multi-class classification problem, binary accuracy is only used for binary classifier, right? So yeah, so we will just use sparse categorical cross entropy instead of binary accuracy. we'll just use accuracy instead of binary accuracy, right? So here, when plotting accuracy over time, change binary accuracy and validation binary accuracy to accuracy and validation. Okay, yeah. So let's train the model, see how it performs. Okay, so 77% accuracy and 76% validation accuracy. Not bad, not bad. I mean, I think here there's not that much overfitting, but let's just look at the plot. Okay, uh, loss function, loss plot, and validation plot. Okay, history. This let's change it to accuracy. Set of binary, change it to accuracy, and validation binary accuracy, change it to just validation accuracy, right? Okay, let's see. Yep, see, training and validation looks smooth. That's a good sign. That means the model is not overfitting. Okay. Okay. Yeah, training started off slightly different, but the accuracy and training and validation accuracy converged quite like converged in the same direction, right? So that's a good sign. Okay, so let's just follow the same stuff and um, evaluate. Okay, so edit vectorizer layer model, there's dot activation sigmoid. Instead of sigmoid we need softmax, right? What? Okay. Oh yeah, it was logits true, right? It was a sparse categorical cross entropy. We need sigmoid. Okay. Yeah, so 73.72% accuracy. And let's throw away some line question, like question. Okay, let's see. Let's create some live question here. Right. So bitwise operation on tensors. This maybe in Python. I'm looking for the example where it doesn't says in Python. So let's see this one. Multi-index. Okay. So let's get it. Okay. So okay, first example. Okay. Oh, okay. It's not a. It's actually a comprehensive question, right? So in this example, you can see planning to quit exception. It's quite a long text, right? So let's just get this one. Okay. Can we just copy it? Okay, there's some new line there. Let's see. let's just grab some question JavaScript. JavaScript stack overflow question. Okay. Yeah, that sounds good. You know what? Let's just do it in triple code. Okay. Then what we have here is this. Let's take this one as well in the triple code. Okay. So this is our examples. Okay. Let's just run prediction on this, right? Okay. Okay. So sigmoid function 0, 1, 2, 4, right? So gives no not, let's just make it softmax because we're dealing with multi-class classification, right? Let's see. So yeah guys, there are some for this one, first one is saying Python, which one is Python, fourth one, right? But it's saying that it's where is it? Okay, this one, right? JavaScript. Okay, so yeah, this one. So if we get the arguments of it, right, arguments of all of it, okay, we need to import numpy as empty. Like let's just let's take it and save it as predictions. Okay, and then what we're gonna do is we'll take the predictions 0 and run np dot arguments on it, right? You can see it's second. So if our class labels is this, then it's recognizing it as JavaScript, the first question, but it's a Python question, right? So if we go ahead and take the first one, still JavaScript 2, still JavaScript 3, still it's C#, okay, 4, it's C#, okay, but it's JavaScript. Okay, so I think the model needs to be trained for more epochs, and definitely the model needs more improvement, right? Because it's not performing quite well on the new data, right? So if you go ahead and test it in test data set, anything like yeah. So if the accuracy is like 73%, then I would assume that it's fitting the model in quite well, but not that great because it's not performing well on the testing, the new testing data, right? So yeah, we will definitely look into the improvement on how to improve the model's accuracy and all, right? So yeah, here's they're saying, so this tutorial introduced text classification from scratch. To learn more about the text classification workflow in general, check out the text classification guide from the Google developers. Okay, so yeah, here we can learn more about the text classification. Okay, yep, nice stuff. I would highly recommend to go ahead and check it and see the room for improvements, right? So thank you guys for joining, and thank you guys for watching this video. I hope you guys learned something, and of course I have definitely learned something. So yeah, thank you guys, and I'll see you in the next video. Bye.